Thanks, Mo, and thank you to the CSI for hosting me today, and thank you all for coming. As Mo said, I'm a brand new faculty member at NC State. I've been there for 4 months, and so it's nice to get out of the office and come out to the coast today and meet everyone. I have to start the talk with a confession. The title's kind of a lie, especially that last part about the Carolina coast. I am not yet running models for the Carolina coast. I've only been here for a couple months. But I am tied in through some of my previous work with the work that has been done here in the state. And so that's these other co-authors are my colleagues in Chapel Hill and in Morehead City. And so the first part of this talk is going to be about modeling in other parts of the country along other coastlines. And then I'm going to try to tie that into some of their work that has been done here in Carolina. So just a little bit about me. Like we said, I'm at North Carolina. I sit in one of the many red brick buildings there and run my computer models. And it's interesting because that's the closest I've ever lived to the coast. Raleigh's 3 hours away. Before that, I was in Austin, Texas, which is 4 or 5 hours away from the coast. And then in Notre Dame is northern Indiana. That's 15 or 20 hours away from the coast. But we were doing hurricane storm surge modeling from there, and especially a lot of applications in New Orleans and Louisiana. And I was lucky in some ways to start at Notre Dame in August of 2005, less than a month before Katrina went through Louisiana and less than 2 months before Rita devastated the coast. My PhD advisor at Notre Dame especially, but also our larger modeling community, had some pre-existing ties to Louisiana and to the Army Corps there in New Orleans. And so we were well positioned to respond after the storm and try to simulate where the water came from, how high it got, and why some of the levee protection systems failed around New Orleans. It's a complicated system, southern Louisiana. There's a lot of features at a lot of different scales. The continental shelf becomes The continental shelf becomes very narrow right near the Mississippi River Delta, which extends pretty far onto the continental shelf. The Mississippi River flows out to the delta past New Orleans. New Orleans is here, nestled into one of the bends in the river. And New Orleans is surrounded on several sides by water. Lake Pontchartrain on the north side, Lake Bourne to the east, some very low-lying coastal marshes to the south and the southeast. So a lot of connectivity, a lot of ways for water to get from the ocean up near the city. And a lot of different scales here. We're really talking about flooding that happened down to very small scales. So these are satellite images of the north side of New Orleans 5 years before the storm, and then this was taken a full 2 weeks after the storm went through. And you can see the difference. These darker areas are the flooding of the neighborhoods on the north side of the city. So this is what we want to model. We want to be able to see how does the water get into these areas through the lake on the north side of the city, through these connectivity out to the deeper ocean. And so we want to be able to model at scales of the Gulf of Mexico, and so several kilometers, but also down to very small scales, and so tens of meters in some of these navigation canals near the city. And we were successful. I don't want to give away the ending, but this is one of our simulations for southern Louisiana and Hurricane Katrina. And so these wind vectors, the arrows are the winds as the storm moves through on its day of landfall, so the 29th of August. And then the colors are the contours of the water levels. And so we're showing that the waters went as high as 8 meters as the storm was making landfall along the Mississippi coastline. You can see the storm surge flooding over this marsh to the southeast of the city and building against the Mississippi River levees. Also here in the confluence of some of the navigation canals, water gets pushed into New Orleans and builds along the north side of New Orleans. And so a lot of different scales here. These are big, high-resolution models that are run on some of the largest supercomputers in the country. And then they were used, as I'll discuss, by the Army Corps and FEMA after the storms went through. And they're used for forecasting of storms here in North Carolina. So like I said, a lot of this talk is going to be about places other than North Carolina, and with a real focus on southern Louisiana, talk about the models that we use and how they work, talk about how they're validated for some of the storms that went through the Gulf and impacted Louisiana, and then move into forecasting and how we're running these models in real time as storms develop and threaten different coastlines, partly in Texas, because I was there the last couple of years, and then partly for how these models are used in North Carolina. So there's a lot of scales that impact this system. We really need to evaluate things out into the Gulf, out into the Caribbean, and out into the Atlantic, because that's where the storms are formed initially, and then they track in and impact our shorelines. So we're talking about circulation and waves being developed in deep water, moving into the Gulf of Mexico and some of the more shallow regions on the continental shelves, moving into southern Louisiana, and a lot of the complexity that I just discussed with the Mississippi River Delta and some of these small-scale, the river and some of the small-scale navigation canals that act as conduits for the water to come up near the city. And then even within the city itself, there's a lot of complexity with the river on the south side, some navigation canals on the east, the big lake on the north side, and then there's some drainage canals that act as fingers down into the city, where the rainwater is pumped out into the lake. So ideally you want water coming from the city out into the lake, but it can go the other way around, and so storm surge can come down into those channels and really threaten inside the city. So we want to resolve all those things in our model, and the way we do that is with unstructured meshes. And so we represent the sea surface with a bunch of triangles, and we can vary the sizes of the triangles depending on how much information we want in those areas. So out in deep water, we use these really big elements. These could be 10 or 20 kilometers on a side, on each side of these little triangles, and then they become progressively finer as you go into the continental shelf and into the near shore and in some of the coastal floodplains. This is actually a really low-res model. What we use nowadays looks more like this. So now I've colored the triangles based on the bathymetry and the topography. You can't see, even at this scale, you can't see the triangles here in the Atlantic. They're too small. And as you go into the Gulf and in the near shore, it looks like just constant contours, because we're just using so many elements to describe what's happening in the Gulf, what's happening in Louisiana, and on into New Orleans. So we've resolved the Mississippi River. We have a description of how flow can get into some of these channels, into the lake, and some of these drainage canals that come into the city. So elements that range from a couple kilometers out in the deeper Gulf down to tens of meters along some of these levee protection systems around New Orleans. So a lot of different spatial scales, also a lot of different temporal scales. So we're interested both in the long waves, so things like tides and storm surge, which have periods of maybe 12 hours or 24 hours, and so that's represented by this wave energy at this temporal scale. But we also want to impact or evaluate the effects of the short waves, so the waves that you would see if you're standing on the beach, the short wavelength waves. And so those have energy that's very different, periods of maybe a second up to 30 seconds. So there's kind of a disconnect here between the long waves that we want to look at in terms of storm surge, and then the short waves that we look at in terms of the wind sea and the swell that impact the system. So we have separate models for that. For the short waves, we use a model called SWAN. We don't represent the individual form of every single wave in the ocean. Instead, we look at this quantity called the action density, and so this is kind of like a wave energy. We have modeled the wave energy as it moves around in the ocean. For the long waves, the storm surge, we use a different model called ADCIRC, and here we are resolving these longer waves, so that a big tide 24-hour wave we can simulate with this model. And the real focus of my PhD was coupling them together so that they would interact. And so the idea here is we run ADCIRC and SWAN at the same time on a big computing cluster. They take turns evaluating the long waves, so the storm surge, and the short waves of the wind sea, and then they pass information back and forth. SWAN passes information about how the waves are breaking in terms of the wave stresses, and then ADCIRC passes wind speeds, mean water levels, current velocities to SWAN. And so the idea here is we can bring in a wind field from anywhere, from the the National Hurricane Center or from some other hindcast of what the meteorology was doing. We use that as forcing to our models. We can evaluate tides. We can bring in the river flow in the Mississippi River or in some other coastal river. We run it on a big computational mesh, and then we have this, we can provide output in a variety of formats. So this all happens on big computing clusters. It's all optimized to run very efficiently, and I'll talk about this a little bit later, but when we run this in real time, the idea is to turn around a forecast in an hour or an hour and a half. So when you have these coupled models, the next thing to do is to validate them, and so the next storm that went through New Orleans was Gustav in 2008. You don't hear as much about Gustav because although it pushed the levee protection system to its limit, it didn't actually fail anything. It came really close. So these are a couple of pictures. This is along an earthen levee. We're looking along the top of a levee here just to the southeast of New Orleans. And you can see on this side, this is the unprotected coastal marsh. The water is within maybe a foot of the top of the levee. There's a little bit of seepage over into the protected area where we have the oil refineries or living neighborhoods. But the levee didn't fail, and so there wasn't widespread flooding. Closer to the city, in the Inner Harbor Navigation Canal, this is one of the concrete flood walls that protect the lower Ninth Ward, the area that was flooded during Katrina. And you can see in the navigation canal, we've got a really choppy storm surge, and again, we're within maybe a foot or two of the top of this flood wall. We have some wave overtopping, and so some water on the protected side, but there wasn't a failure. There wasn't the widespread flooding of Katrina. Gustav was a little bit weaker of a storm, and it tracked just a little bit farther away, and so it didn't threaten the city as much as Katrina did. And so we were successful here too, and so this is kind of a similar animation to what I showed before, but you can see the water moving over this Carnarvon Marsh and eventually pushing against this earthen levee, but not failing it. Water moves into the confluence of the Mississippi River Gulf Outlet and the Gulf Intercoastal Waterway, and really threatens these levees near the downtown of New Orleans. Water is pushed away for most of the storm from the north side of New Orleans and the protection system against Lake Pontchartrain. But really a lot of resolution here, a lot of accuracy in terms of modeling where the water went and when it did. One way to validate our models is to compare with high water marks, and so what we're showing here is a comparison with all the high water marks that were measured after Gustav, and the color scheme is the difference between our AdCirc simulated results and what was actually measured. So points that are green are showing a match between our prediction and reality within a half a meter. Points that are, when warmer colors, indicate regions where our models were too high. Cooler colors like the blue and the purple are regions where our models were too low. And most of these points are green, showing a very good match between our model simulation and what actually happened in southern Louisiana. Another way to look at these is in a scatter plot, and so here we're showing modeled high water marks on the vertical axis and measured high water marks on the horizontal axis. If you have a perfect model, then everything is going to come onto this diagonal, right? There would be a perfect match between our model and our measurements. And we get pretty close. A lot of these points are green, and so they're clustered here within a half a meter of a perfect match. And the same was true for all four storms. So Katrina and Rita in 2005, Katrina with high water marks that go up, more than 8 meters, and then Gustav and Ike in 2008. Katrina and Gustav impacted southeast Louisiana. Rita and Ike were more to the west. Ike actually made landfall in Texas. But in this Louisiana model, there was still quite a bit of flooding in southwest Louisiana, and we're showing a good match to the data. So we have a good description of southern Louisiana. We have validated for several storms, and so the next thing to do is to use it for some actual engineering. And we did that with several projects. One was tied in with the U.S. Army Corps, reevaluating the surge barriers around New Orleans and eventually designing a new one. So one thing that happens during these storms is a lot of times the wind is blowing out of the east. You get a lot of storm surge pushing over Lake Bourne and into the confluence here of these navigation canals, and then really threatening the levees inside the city. And so what the Army Corps has done is built a new surge barrier right here at the confluence. And for most of the time, these gates are open to allow shipping to come in and out of the city. But as the storm waters increase, you can close them. This was a $15 billion project that was completed before last hurricane season, and it was informed partly by the results of our models. Another application was our work with FEMA to redo the floodplain risk maps, starting in the Gulf, but now they're going up the Atlantic seaboard into Virginia and New York and the upper Northeast. So the idea here is not to use any historical actual storm, but to run a bunch of fictional storms, all with different tracks, different intensities, different forward speeds, each one impacting the coastal flooding in a different way, and then to synthesize those results to develop the 100-year flood maps for the entire coast. And so, for example, one of these storms, so storm number 265, might have a track that looks very close to what happened during Rita, with all the flooding of southwest Louisiana that happened during that storm. But this was a different synthetical storm, a fictional storm with a different radius to max winds and a slightly different track. And so the results from this storm surge, this coastal flooding, would be combined with the results from all the other synthetic storms statistically to develop the 100-year flood maps for southern Louisiana. And this same system's been used for Texas and all along the Gulf and then all along the Atlantic coast. Another obvious application is hurricane forecasting. And for that, we use something called the ASGS Surge Guidance System. And that was developed here in North Carolina by my colleagues at UNC Chapel Hill. And the idea here is to run everything automatically. If everything's working correctly, we as modelers don't have to do anything but just watch the emails go by. The wind fields are pulled down automatically from either INCEP within NOAA, or during a hurricane, we pull down the advisories from the National Hurricane Center and then generate wind fields on the fly. And then the guidance, the forecast guidance of the coastal flooding can be shared in several different formats, and I'll go through that a little bit later. So returning to this flow chart, the same thing happens. We're running both ASGS for the long waves and SWAN for the short waves, doing our coastal flooding predictions and then sharing our output. But this time it's all handled automatically. We have scripts that run on these HPC clusters, and so they sense automatically when the next advisory comes. They build the wind files, they run the model, and then they share the output via email. And if you don't have any bugs in your system, then it can all be done without you actually sitting at the computer, which is nice because every 6 hours they're issuing another advisory from the National Hurricane Center, and it's nice to be able to handle these things without too much effort on our part. There's several teams that run the ASGS Surge Guidance System, the ASGS. The primary developers are at UNC Chapel Hill, and so their focus is on Carolina and the surrounding states here. LSU, there's a team that runs the system for the Northern Gulf. And then I was running the system in Texas for the Texas coastline, and we were sharing our results with the state level operations center, and then they were forwarding that guidance down to the local levels. And so during the 3 years that I was in Texas, there wasn't a storm that impacted our coast, but we did run our system as a test during Isaac, which actually made landfall in Louisiana. So I wanted to show a little bit about that here. Isaac was an interesting storm. It never got to be very powerful. It moved through the Gulf, and right before it made landfall, it became a hurricane, a Category 1. It had a very low central pressure. It could have been a Category 2 or a Category 3, but the core just never came together, and so they couldn't move it into one of those classifications. There was it was a very slow storm. It made landfall and then just kind of sat there on the coast and was a big rainfall event for a lot of southern Louisiana. 20 inches of rainfall fell in New Orleans, 10 inches along the Mississippi coast. And because it was just sitting there without really moving into the coast, it had a lot of time to drive surge over the coastal wetlands and the marshes. And so they had 3.5 meters of surge just southeast of New Orleans and Shell Beach. So it wasn't a powerful storm, but because of its track, and especially because it made a very slow landfall, it did threaten some of the protection systems around New Orleans. And so there wasn't any flooding in New Orleans, but because of all of the improvements that they've made to the protection system, but some of the surrounding communities did have some levee overtopping, and I'm sure you remember this from a year ago, and some of the flooding that happened just outside of New Orleans. It was an interesting storm because it had a lot of uncertainty in its track. It started out in the Caribbean Sea, and for a long time they thought it was going to make landfall on the Florida Panhandle. And in just 2 days before it actually did make landfall, those tracks started to shift westward toward Louisiana. And you go from, in Louisiana, from their perspective, you go from an event that's not really that much of a threat. You're on the west side of the track, you're not going to get much storm surge, to in 2 days' time having a direct hit from a hurricane and really being threatened by storm surge. And so I just want to walk you through some of these advisories that we were putting out. These are the wave heights, and so this is the wave environment inside the Gulf. Wave heights up to 12 meters we were predicting. This is one of the early advisories, so about 2 days before landfall, when the track was just along the Florida border. You're seeing not much wave action around Louisiana because it's west of the track. The next day, the track shifted over to Louisiana, and now you've got 10 or 12 meter waves breaking outside the Mississippi River Delta, moving onto the shelf and breaking along the Chandelier Barrier Islands, and quite a bit of threat to Louisiana. And then as the storm moves closer, they started to realize it's not actually going to become as powerful of a storm as we thought. And so these wave predictions become a little bit less. The winds are not quite as strong here. We know a little bit more about the storm. But the track here is settled on Louisiana by Advisory 28. These are the water levels, and so this is one of the formats we were sharing with our partners there in Texas. So we visualized our model results and then put them into Google Earth. And so this is nice because the emergency managers, if they want to, they can use this and zoom in and see what's happening in different areas. This was Advisory 28 right before the storm made landfall, and so we're showing water levels up to 8 or 10 feet here in Lake Borgne, so just east of New Orleans. And you can really see how the predictions changed over the time of the storm. In Advisory 20, when the storm was predicted to make landfall in Florida, we're not showing much impact at all in Louisiana. The next day, the track had moved over to Louisiana, but they were over-predicting how strong the storm would be. And so here we're showing 12 feet or more of water in Lake Borgne. And finally, we settle on a more accurate prediction because the wind forecasting has become more accurate this close to landfall. If you zoom in on this location, Shell Beach, and plot out all of our predictions in the light gray and then what actually happened in the black, you see earlier in the storm, when it wasn't predicted to make landfall in Louisiana, we were showing a maximum water height of just 1.5 meters. Later on, when it was predicted to make landfall, but as a very strong storm, we're showing really big peak water heights up to 4.5 meters. And then we settled down closer to reality as the storm was making landfall. So a nice envelope, I guess, of what could happen here depending on the track and the strength of the storm. Sorry, I'm sorry about that. Here in North Carolina, the results are shared in a little bit different format. It's done on a website, so you can go to this address, and I'll come back to this a little bit later. And so they're running their models every day. Even if there's not a storm, they can still pull down wind forecasts from just the base meteorology and then use those to force our models. And then present them in this way for anyone who wants to go and see what might be happening in terms of the waves and the coastal flooding along the state coastline. It's nice, it's updated every day, depending on it, no matter if there's a storm or not. It's integrated within Google Maps, and so you can go in and click and see what's happening wherever you want. They're showing results in terms of water levels above mean sea level or just above the local ground level. They're showing information about the significant wave heights and the peak periods from the forecasts, the wind speeds, and then also some selected hydrograph information at some of the NOAA stations. To describe, and I'm sorry about this, this is kind of a dark satellite image, but to describe the Carolina coast, they have their own unstructured mesh, and it's kind of hard to see at this screen brightness, but we've got triangles out that are larger out in deep water, and we're making them small and really resolving the coastlines as we go through, starting down in South Carolina and then moving up into Virginia, but with a real focus on flooding of the Carolina coast. And so I want to actually pull up the website and click around and show you what all is available. So this is a hindcast during Irene, which moved through in 2011, showing the maximum water levels. And there's a nice scale here on the right side. Oh, this is not going to work. Okay. Sorry about this. So in feet and meters, and show this is what's showing what happened during Irene. Irene, as you know, tracked over the sound and pushed a lot of water over the barrier islands and then into some of these back bays. We're showing 8 or 10 meters, 8 or 10 feet of water flooding up some of these river systems. But the nice thing is you can move around and zoom out if you want to look at significant wave heights instead during the storm. That's pretty nice. And some of the later results, like Sandy, so from last year, Sandy was tracked a little farther away from North Carolina, but obviously devastated the New Jersey coastline. It's always tricky when you want to run these things interactively during a presentation. But I really want to show you what's available and what we're doing. And so right now, this is going to be an animation of the wave heights as the storm moved through the system. And so now it's a little farther away, but what's happening is, as we're going through, for every time series, as we've gone through the simulation, we're visualizing the wave forecast during the storm and showing how it's evolving as the storm moves along its track. So this is information not just showing the maximums of what could happen in terms of the wave heights or the coastal flooding, but really showing in time what's happening. And so these wave heights get to be very large as the storm turns and makes landfall there in New Jersey. Come on. Well, and so I encourage you to go to this website. You don't have to remember this whole thing, but ncera.renc.org will take you to this page, and you can click around. They have the historical storms there, but you can also bring up just forecast by day.
The link below the rebroadcast of this on our website.
That'd be great. Yeah. Yeah. So everyone could go and see what's available out there. You can also select by day and see the forecast for specific times. And so this is one of the forecasts during Sandy, but you could pull up the forecast for today. The model was run this morning and see the wave heights, and there's no storm, and so there's not going to be as much interesting waves and coastal flooding, but you can see them as you go through the day. So in conclusion, I've been directly involved with developing these models and validating them for Southern Louisiana. A lot of that technology has been shared and is now being used in North Carolina. And then they shared with me the forecasting system. I was running it in Texas, and I'm very excited about contributing to that effort and helping improve what's going on here in the North Carolina region. So thank you for your attention, and I'm happy to answer any questions now if you have them.
have plenty of time.